In this video, we're going to do a few extra examples using the principle of inclusion-exclusion, or what we call pi. So again, these, if you've gone further in the videos, these could be done using Venn diagrams as well, but they just need the principle of inclusion-exclusion, so we can do them without the picture, which is what I'm going to do here. So in the first example, we want the number of S intersect T, given that the number of elements in S is 4, the number of elements in T is 12, and the number in the union of S and T is 15. So this is a little bit strange because they gave us the union, but they're asking for the intersection. So we just need to remember the formula is the number of things in the union is the number of things in S plus the number of things in T minus the number of things in the intersection. So if you think about it, we have this one, we have this one, and we have this one, and this is the one that we want. So if you're ever just missing one thing, you can always just rearrange to find it. Okay, so that means if I just plug in the numbers, so this should be 15 is equal to 4 plus 12 minus the thing that I'm actually looking for. So the number in S intersect T. So that means that 15 is equal to 4 plus 12 is 16 minus the number in the intersection. So if I add the number in the intersection to both sides, so that it's positive. I mean, you might be able to see what the number should be already. And then I subtract 15 on both sides. Those are going to cancel out. And that's going to tell me that the number in the intersection, S and T, is 16 minus 15, or 1. So there was one thing that was in both S and T in order for all of these other things to be true. Okay, let's see a word problem here. So suppose that all of the 1,000 first-year students at a college are enrolled in either math or English. You also know that 400 of them are taking both a math course and an English course, and 600 are taking an English course. We want to know how many are taking a math course. So I'm going to just define some notation. So let's let E be the set of students in an English course, and M be the set of students in a math course. Okay, and then I want to think, what did they actually give me? Okay, so the easiest one to see is this thing here. 600 are taking an English course. So I know the number in E is 600. Okay, so that one is pretty straightforward. Oops. Okay, and then I also know 400 are taking both math and English. Okay, so what that tells me is that the number in the intersection should be 400. Okay, now if you think about the formula for pi, there's 4 things in it, and so far we only have 2. So the thing that is least obvious is this first statement up here. All of the 1,000 students at the college are enrolled in either math or English. That's actually giving us the union. So the number in the union is 1,000. Because all of these 1,000 students are in at least one of math or English course. Okay, and then what we want is the number that are in math. They could be taking English as well, but we just want to know how many are taking a math course. So we can use the principle of inclusion-exclusion. So we know the number in E union M is the number in E plus the number in M minus the number in E intersect M. And now if I put all these numbers in, that's 1,000 should equal, oops, not 400, 600 plus the number in M minus 400. So 600 minus 400 is 200. So 200 plus the number in who taking a math course should equal 1,000. So you can probably see the number that are taking a math course needs to be 800. Okay, and you should answer this maybe with a sentence. So there are 800 students taking a math course. Okay, now some of these are also taking English. Okay, in fact, 400 of them are also taking English. Okay, one more. So of the 26 capital letters in the English alphabet, 11 have vertical symmetry, 9 have horizontal symmetry, and 4 have both. Okay, and they've given the examples here. So I guess maybe vertical symmetry means that if you have a vertical line down the middle, they're the same on both sides. Okay, horizontal symmetry, if you have a horizontal line down the middle, they're the same top and bottom. So now these guys here are the same vertically and horizontally. Okay, so again, some notation. So let's let H be the set of letters with horizontal symmetry, and V be the set of letters with vertical symmetry. Okay, so then what did they give us? 11 have vertical symmetry, so that's the number in V. 9 have horizontal symmetry, so that's the number in H. And 4 have both. So that's V intersect H is 4. Okay, and then what they want is how many letters have no symmetry. Okay, so this is not the union. So the union, so that just think here. Okay, so V union H is the set of letters with at least one of the symmetry types. Okay. So if I want to know how many have no symmetry, I want to know how many are not in the union, right? Because the union has all the letters that have some symmetry. So what we want is the number in the complement of the union. Okay, so we can find that by first finding the number in the union. So the number in the union is the number in V plus the number in H minus the number in the intersection. So that's 11 plus 9 minus 4. So that's 16. Okay, so there's 16 letters that have some symmetry. So that means that the number in the complement of this, using the complement rule, should be the number in the universe minus the number that have some symmetry. So the universe is all 26 letters. There's 16 that have some symmetry. So that means there's 10 that have none. Okay, so then we can say there are 10 letters with neither of the symmetries. Okay, so you can find how many do have some symmetries and then take the total minus that to get how many have none of the symmetries. So that's a few examples using the principle of inclusion and exclusion.